All right, so this is the answer. Okay, so you're thinking of this. The radius, okay, the rho, okay, rho goes from 0 to whatever, okay, and this is where z is equal to 1, right? And so that's the key picture here. You have theta, this is 1, and so the question is how long the rho goes from 0 to until it hits the horizontal line z is equal to 1. So you have to somehow express, here's the question, right? Z is equal to 1. How do I do that? Well, just think about this here, right? Because what we have is this triangle. This is rho. This is what you want to express, okay? And this is 1, and this is phi, all right? How are they related to each other? Well, it looks like 1 over rho is some kind of a trigonometric function of phi. 1 over rho turns out to be the opposite, adjacent over the hypotenuse. That is the cosine of phi, right? So if you think about this, rho is of course, you can take the inverse or the reciprocal of each. It's 1 over cosine of phi, which is called a secant of phi. Okay, and that is exactly what you need. Rho expressed as a function of phi is a secant of phi. All right, so the volume of this cone turns out to be the integral from 0 to pi, 2 pi, 0 to pi over 4, and then from 0 to secant of theta, rho square sine phi d rho d phi d theta. Okay, so that is the way to express that. You want to go ahead and try this? You can, I think most students actually have no problem evaluating the triple integrals. It's this part that is the most difficult part of this problem. Okay, how do you write the volume? Right? How do you express rho going from this point to this point? Well, the answer depends on phi. So let's try to find that as a function of phi. And it turns out to be a pretty simple trigonometry. I mean, this is a pretty simple trigonometry, right? But that's what you would need to find the upper bound for rho. Once you have done that, it's not too bad, right? Because this is what you'll end up with. It's 1/3 rho cubed going from 0 to secant. Okay, maybe this one is kind of hard because you still have secant square or secant cube or something here, right? All right, so this is what you'll end up with. The rho, let's see. I'm talking and writing at the same time. It's hard to do. All right, so you can erase that. And so this, you have sine of phi still here. Okay, and then here. Okay, so this, of course, I'm going to take this 1/3 into the front, okay, and then you have secant cubed, and then you still have sine of phi as a part of your integrand. And so what is sine, what's secant? So secant is 1 over cosine, right? So you have 3 of these, and then you have sine of these, right? So why don't we write this as something like this? Sine phi is on the top. Just let's borrow one of these cosines here. Right? This is a little simpler. What you have here is basically this, and you can read this as secant square times tangent to the first degree, right? So that's what you have. And so now you have to think, right? So this is tangent times secant square, and you can do a u substitution. U is tangent theta. Don't you love u substitution, right? U is so wonderful. U is my sunshine, my only sunshine. Du is secant square theta. How convenient, okay? And so this just becomes, and by the way, everything else has to be changed here, the upper limits and so on. So instead of theta going from 0 to pi over 4, the tangent of 0 is 0. Tangent of pi over 4 is, yeah, nice, right? And so this becomes u, and then of course secant square I think I misspelled. This is called a Greek typographical error. I kind of messed up on that. So I should have had phi and not theta here. That happens. Okay, so since this and this combined together is du, I have du here and d theta, and the tangent of, this is tangent of phi, right? Tangent of phi is here, and that's of course my u. And so this is also phi. And so that I think takes care of my mistakes here. This is 1/3 pi over integral from 0 to 2 pi. And then this just becomes u squared over 2, right? And then you integrate from 0 to 1. All right, so this is 1/3 and then 1/2 2 pi. And of course, this is just 1/3 pi, or pi over 3 is the answer to the question. That is the volume of this cone with a flat head. Now, you could also have found this in a couple of different ways, all right? So right at the end of this, let me just show you, because I think it's important for you to be able to express this in several ways. One way to think about this, you have a height 1 and then the radius 1 cone, right? So in cylindrical, this is actually not bad, right? So 0 theta 2 pi, the theta goes from 0 to 2 pi. And then r goes from, if you look at this from the top, of course, all you see is that, right? So r goes from 0 to 1. Now, once you pick a particular theta and a particular r, okay, then you have to figure out z goes from what to what, all right? And remember, this is the cone, 45-degree angle cone, so z is equal to r. Okay, so z actually goes from r to 1. So z goes from r to 1. It doesn't go from 0 because 0 is down here, right? And this is, like what appears to be like a cone, sort of like your coffee dripper. And so it goes from this point r all the way to when z hits 1. And so if you set this up in a cylindrical coordinate system, it's going to be a little easier, because see, the flat top is not very friendly to spherical coordinate system, but it is friendly to cylindrical, or you could say cylindrical coordinate system is more friendly to a flat top than the spherical coordinate system is. So this goes from 0 to 2 pi, this goes from 0 to 1, and then r to 1, r dz dr d theta. Okay, you want to go ahead and do this? Yes, you do, because you're a calculus student and you look forward to doing problems. When you do dz, there's nothing here, so it just becomes 1 minus r, that's these numbers. R is already still here, and it's not going to go away, and not yet, right? So this is r minus r squared. That's what you're integrating. Okay, and so this goes from 0 to 2 pi of r squared over 2 minus r cubed over 3, 0 to 1, this is r to the cube power, right? Okay, and then you have the theta, but that is 1/2 minus 1/3, right? And then you just have 2 pi at the end. So this is 1/6 times 2 pi, and of course that is pi over 3, as we expected. All right, finally, there's one more way, and of course this is the easiest way to find the volume of this, right? I mean, this is a cone. You knew the equation from your geometry class for the volume of the cone, right? So this cone is basically the same cone as this. It's radius 1, height 1. So what's the volume of this cone? It is 1/3 times pi r squared times h, right? Well, height is 1 and the radius is 1. So this is 1/3 times pi, 1 squared times 1. And of course, that's pi over 3. Okay, so we were right 3 times, and that makes you feel good, I think. All right, I hope you got that. Okay, so some of these integrals will be complicated to set up. And for your homework, some of the problems, unfortunately, will give you some messy calculations, but don't let that bother you. What you want to understand is to gain is the conceptual understanding of how to set up cylindrical and spherical triple integrals, right? And you know, if calculations get messy, just go ahead and do this, because for homework, I give you more challenging problems than what you will see on your exams. All right, so don't get overly frustrated, but do get a slightly frustrated, just enough so you have resistance to build your calculus muscles. Okay, so I hope you will have fun doing your homework from section 5.5. And next we'll go into 5.6, some applications of double and triple integrals. All right, until then, I hope you have a great week. Talk to you later. Bye.